NEC Section 220.21 permits the application of diversity factors for elevator loads when sizing the service overcurrent protective device. This is based on the premise that all elevators in a group are unlikely to operate simultaneously. Table 620.14 provides diversity factors for various types of load-on feeders. While this table is typically used for feeders, it can be used as a basis for determining a diversity factor for elevator loads and sizing the service overcurrent protective device under certain conditions. To use Table 620.14 for this purpose, the following conditions must be met. Firstly, the elevators must be duty rated based on the expected operating conditions, including anticipated peak usage and duty cycle. Secondly, the elevators must be installed and operated according to the manufacturer's instructions. And thirdly, the elevators must be maintained and inspected regularly to ensure reliable operation. If these conditions are met, the diversity factor for elevators can be calculated using Table 620.14. The appropriate diversity factor is based on the elevator rating and the number of elevators in the group. As an example, consider a service with 20 elevators, each rated at 1000 amps. According to Table 620.14, the diversity factor for 20 loads rated at 1000 amps is 0.75. The main service overcurrent protective device can then be sized using the following formula: main service overcurrent protective device equals total elevator load times diversity factor. Main service overcurrent protective device equals 20 times 1000 amps times 0.75, which equals 15,000 amps. Under the specified conditions, NEC Section 220.21 permits the use of diversity factors for elevator loads and size in the main service overcurrent protective device. Table 620.14 can be used as a basis for determining the appropriate diversity factor. This method provides a practical approach to account for the unlikely occurrence of simultaneous operation of all elevators. When dealing with electrical systems and specifically elevator loads, understanding and applying the National Electrical Code, or NEC, correctly is essential for safety and efficiency. The NEC provides guidelines on how to properly size electrical services, including the overcurrent protection. Elevators, being significant electrical loads, require careful consideration in service calculations. One key aspect is the concept of diversity, which recognizes that not all loads operate at their maximum simultaneously. NEC Section 220.21 addresses the application of diversity factors, allowing for a more realistic assessment of the total load. This is particularly relevant for elevator systems where multiple units are unlikely to operate at full capacity concurrently. This section allows for the reduction of the total calculated load based on the understanding that not all elevators will be running at their peak demand at the same time. Table 620.14, while primarily intended for feeder calculations, offers valuable insights into diversity factors for elevator loads. Feeders are the conductors that carry electricity from the service equipment to a subpanel or a specific load, such as an elevator. This table provides diversity factors based on the number of elevators and their individual load rating. Using Table 620.14 as a basis for service calculations involves understanding its limitations and ensuring that the specific conditions of the installation align with its intended application. To use Table 620.14 effectively for service overcurrent protection sizing, several conditions must be met. Firstly, it's essential to ensure that the elevators are duty rated according to their expected operating conditions. This means that the elevators must be designed and rated to handle the anticipated peak usage and duty cycle, including the frequency and duration of operation. Secondly, the elevators must be installed and operated following the manufacturer's instructions. Correct installation is crucial for ensuring that the elevators operate safely and efficiently and that their electrical characteristics align with the assumptions used in the diversity factor calculations. Thirdly, regular maintenance and inspection are necessary to ensure the elevator's reliable operation. Consistent maintenance helps prevent unexpected failures and ensures that the elevators continue to operate within their design parameters. When all these conditions are satisfied, Table 620.14 can be used to determine the appropriate diversity factor for the elevator loads. The diversity factor is selected based on the number of elevators and their individual ratings. It's a multiplier that reduces the total calculated load to account for the non-simultaneous operation of the elevators. For example, consider a building with 20 elevators, each rated at 1000 amps. According to Table 620.14, the diversity factor for 20 loads rated at 1000 amps is 0.75. This means that instead of calculating the service load based on all 20 elevators operating at 1000 amps simultaneously, the total load can be reduced by applying the 0.75 diversity factor. The formula for calculating the main service overcurrent protective device size is main service overcurrent protective device equals total elevator load times diversity factor. In this example, the calculation would be main service overcurrent protective device equals 20 times 1000 amps times 0.75, which equals 15,000 amps. This calculation provides a more realistic estimate of the actual load demand, allowing for a more appropriately sized service overcurrent protective device. The service overcurrent protective device, or OCPD, is a critical component of the electrical system. It's designed to protect the electrical system from overloads and short circuits. Properly sizing the overcurrent protective device ensures that it can handle the expected load while still providing adequate protection against faults. Using diversity factors to size the service overcurrent protective device can result in significant cost savings and improved efficiency. By reducing the calculated load, the size of the service conductors, overcurrent protective device, and other electrical equipment can be optimized. This not only reduces the initial cost of the installation, but also lowers the ongoing operating costs by minimizing energy losses. The application of diversity factors for elevator loads is a practical approach to electrical service design that aligns with real-world operating conditions. By considering the likelihood of non-simultaneous operation, the electrical system can be designed to be both safe and efficient. However, it's crucial to adhere to the NEC guidelines and ensure that all conditions for using diversity factors are met. Furthermore, consulting with a qualified electrical engineer is recommended to ensure that the electrical system is properly designed and installed. Electrical service design for buildings with multiple elevators requires careful consideration of various factors to ensure safety, reliability, and efficiency. The National Electrical Code, or NEC, provides the framework for these designs, but understanding and applying its provisions correctly is essential. One of the key considerations is the calculation of the total electrical load, which must account for all the electrical equipment in the building, including the elevators. Elevators are significant electrical loads, and their impact on the service calculation must be carefully evaluated. However, it is unlikely that all elevators in a building will operate at their maximum load simultaneously. This is where the concept of diversity comes into play. Diversity allows for a reduction in the total calculated load based on the understanding that not all loads will operate at their peak demand at the same time. NEC Section 220.21 specifically addresses the application of diversity factors for elevator loads. This section recognizes that the simultaneous operation of all elevators at their full rated load is improbable and permits the use of diversity factors to reduce the calculated load accordingly. This can result in significant cost savings by allowing for a smaller service entrance and associated equipment. Table 620.14 provides guidance on diversity factors for elevator loads. While this table is primarily intended for feeder calculations, it can also be used as a basis for determining diversity factors for service calculations, provided that certain conditions are met. The table provides diversity factors based on the number of elevators and their individual load ratings. The diversity factor is a multiplier that reduces the total calculated load to account for the non-simultaneous operation of the elevators. To use Table 620.14 for service calculations, it is essential to ensure that the elevators are duty rated according to their expected operating conditions. This means that the elevators must be designed and rated to handle the anticipated peak usage and duty cycle, including the frequency and duration of operation. It is also important to ensure that the elevators are installed and operated following the manufacturer's instructions. Correct installation is crucial for ensuring that the elevators operate safely and efficiently and that their electrical characteristics align with the assumptions used in the diversity factor calculations. Regular maintenance and inspection are also necessary to ensure the elevator's reliable operation. Consistent maintenance helps prevent unexpected failures and ensures that the elevators continue to operate within their design parameters. In addition to the NEC requirements, it is also important to consider any local codes or regulations that may apply to elevator installations. These codes may have additional requirements or restrictions on the use of diversity factors. When calculating the service load for a building with multiple elevators, it is important to consider all the factors discussed above. This includes the NEC requirements, the elevator duty ratings, the manufacturer's instructions, and any local codes or regulations. By carefully considering all these factors, it is possible to design an electrical service that is safe, reliable, and efficient. Here is a more detailed breakdown of how to apply these concepts to a real-world scenario. Let's assume a building has 20 elevators, each with a rated load of 1000 amps. The first step is to determine the total connected load of all the elevators. This is simply the sum of the individual elevator loads, which in this case is 20 elevators times 1000 amps per elevator, which equals 20,000 amps. The next step is to determine the appropriate diversity factor to apply. According to Table 620.14, the diversity factor for 20 elevators is 0.75. This means that the total calculated load can be reduced by 25%. To calculate the total demand load, multiply the total connected load by the diversity factor. In this case, the total demand load is 20,000 amps times 0.75, which equals 15,000 amps. The service entrance and associated equipment should be sized based on this demand load. This will ensure that the electrical service is adequate to meet the building's needs without being excessively large or expensive. In addition to the elevator loads, it is also important to consider the other electrical loads in the building, such as lighting, HVAC, and receptacles. These loads should be added to the elevator demand load to determine the total service load. The service entrance and associated equipment should be sized based on the total service load. Remember, it is always best to consult with a qualified electrical engineer when designing an electrical service for a building with multiple elevators. An experienced engineer can help ensure that the electrical service is safe, reliable, and efficient. The electrical system design for buildings with elevators involves a multifaceted approach to ensure safety, reliability, and energy efficiency. The National Electrical Code, NEC, serves as the primary standard for electrical installations, dictating how to properly size and protect electrical systems. Elevators present unique challenges due to their dynamic loads and critical operational requirements. Therefore, a thorough understanding of the NEC and elevator-specific considerations is essential. One of the fundamental aspects of electrical design is load calculation. This process involves determining the total electrical demand of the building, including lighting, HVAC, receptacles, and elevators. Elevators, with their large motors and intermittent operation, can significantly impact the overall load. However, it is unlikely that all elevators in a building will operate at their maximum load simultaneously. This principle of non-coincidence is the basis for applying diversity factors. Diversity factors are multipliers used to reduce the calculated load to account for the fact that not all loads will operate at their peak demand at the same time. NEC Section 220.21 specifically addresses the application of diversity factors for elevator loads. This section recognizes that the simultaneous operation of all elevators at the full rated load is improbable and permits the use of diversity factors to reduce the calculated load accordingly. The NEC provides guidance on appropriate diversity factors for different types of loads. However, Table 620.14 offers more specific diversity factors for elevator loads. This table is primarily intended for feeder calculations, but it can also be used as a basis for determining diversity factors for service calculations, provided that certain conditions are met. The diversity factors in Table 620.14 are based on the number of elevators and their individual load ratings. The table provides a range of diversity factors depending on the specific application. To use Table 620.14 for service calculations, it is essential to ensure that the elevators are duty rated according to their expected operating conditions. This means that the elevators must be designed and rated to handle the anticipated peak usage and duty cycle, including the frequency and duration of operation. It is also important to ensure that the elevators are installed and operated following the manufacturer's instructions. Correct installation is crucial for ensuring that the elevators operate safely and efficiently and that their electrical characteristics align with the assumptions used in the diversity factor calculations. Furthermore, regular maintenance and inspection are necessary to ensure the elevator's reliable operation. Consistent maintenance helps prevent unexpected failures and ensures that the elevators continue to operate within their design parameters. Overcurrent protection is another critical aspect of electrical system design. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. Properly sizing the overcurrent protective devices ensures that they can handle the expected load while still providing adequate protection against faults. The NEC provides detailed requirements for overcurrent protection, including the selection and sizing of overcurrent protective devices. The size of the overcurrent protective device must be coordinated with the size of the conductors it protects. The conductors must be able to carry the load without overheating, and the overcurrent protective device must be able to trip or blow before the conductors are damaged. In addition to overcurrent protection, ground fault protection is also important for elevator systems. Ground fault protection is designed to protect people from electric shock by detecting and interrupting ground faults. A ground fault occurs when electricity flows to ground through an unintended path, such as a person's body. Ground fault protection is typically provided by ground fault circuit interrupters, or GFCIs, or ground fault protective equipment, or GFP. GFCIs are required in certain locations, such as bathrooms and kitchens, where there is a high risk of electric shock. GFP is typically used for larger electrical systems, such as those found in commercial buildings. Energy efficiency is also an important consideration in electrical system design. Energy-efficient electrical systems can save money on electricity bills and reduce the environmental impact of the building. There are many ways to improve the energy efficiency of electrical systems, such as using energy-efficient lighting, installing variable frequency drives, or VFDs, on motors, and using power factor correction capacitors. VFD can save energy by controlling the speed of motors to match the load requirements. Power factor correction capacitors can improve the power factor of the electrical system, which reduces energy losses. The NEC provides guidance on energy efficiency, including requirements for energy-efficient lighting and motor controls. By following the NEC requirements and implementing other energy-efficient measures, it is possible to design electrical systems that are both safe and energy efficient. Finally, documentation is an essential part of electrical system design. Accurate and up-to-date documentation is essential for the safe and efficient operation of the electrical system. The documentation should include a complete set of drawings, including the electrical plans, wiring diagrams, and equipment schedules. The documentation should also include a written description of the electrical system, including the design criteria, load calculations, and overcurrent protection scheme. All documentation should be kept in a safe and accessible location. In summary, electrical system design for buildings with elevators requires a comprehensive approach that considers safety, reliability, energy efficiency, and documentation. By following the NEC requirements and implementing best practices, it is possible to design electrical systems that meet the needs of the building while protecting people and property.